Okay, so for our next lesson on networks, we're going to talk about drawing a network diagram, both from tables or from situations. First thing, I've got a couple of terms there, which I think we dealt with in the last lesson. I think actually at that time I said I thought I'd dealt with them before, but it's only because I looked ahead. So a connected graph, that's where we talked about Hobart, for instance, is not connected by road to the road network in Australia, in the mainland of Australia. So a connected graph is one where I can get from any one vertex to any other vertex. So, for instance, if I was talking about the 5 most populous cities in New South Wales being connected by railway links, it doesn't matter if there's not a direct line between, say, Newcastle and Wollongong. Maybe I've got to go through Sydney to get there, but that's okay as long as I can stay on the railway lines and get between Newcastle and Wollongong. Newcastle and Wollongong are connected. All right. And a traversable graph, that's where we think about basically travelling along all the edges exactly once without taking your pen off the paper. So the example I gave last lesson was to look at some of the capital letters, and we'll do a bit more with that a little bit later. And the next term that we need to think of today is isomorphic. Isomorphic just means that you've got the exact same network, it's just been represented differently. And one of the great ways to play around with isomorphic graphs is to make your network graphs in GeoGebra. You'll probably find maybe for some of you in the assessment task, using GeoGebra will be an easy way to deal with things. It's a great way of being able to rearrange stuff. So we're going to start there today. And we've got this basic little network here with an A in the middle and then B, C, D, E around the outside. So we're going to draw that up in GeoGebra. So we're just going to zip across here to geogebra.org. And when you get into this window, the best place to go is to GeoGebra Classic. There's a few other apps around, but GeoGebra Classic would be the best way to go. When we get into GeoGebra Classic, we'll get a few options come up, some that we don't need. When we're drawing network graphs, we probably don't want this axis and we probably don't want that the grid. So we just press over here and we hide the axis. And if we press on the grid, we can choose all different manner of grids, but we can also choose to just not have grid. Okay. Now, when drawing vertices, when drawing networks, the best thing to use is the point to make your vertices. And in the line graph, so when you click on these, you get menus. So you can choose a point there. And when you want to join your vertices together with edges, use the segment option. So we're going to start first, and it always labels them in alphabetical order. So it was A, B, C, D, E. While I've got that tool selected, it'll just keep making dots for me. Now that I've got all the necessary vertices, I can go and make some segments. Now in that particular one, all the edges around the outside were joined, and you just press on the dot and then press to the next dot to make a segment that joins the two. Importantly, when you join them to the right dots, they're going to, even if you move things later, the edges will follow the vertices where they go. And this allows us to see isomorphic graphs really easily. So that's pretty much the picture we had back on our theory booklets. It has gone along and labelled all of these edges. Now, I may not want it to do that. I can click on the edge here and choose my settings, and I can actually choose to tick off to show label. The other thing I can do, for instance, I'll do that with G here, is I can put a number here. Why would I put a number there? When I do that, usually it'll choose, you don't change the name of the edge, you change its caption. If you put a caption there, it usually automatically updates and puts the caption there. So if I wanted to do a weighted edge, that's how I would do that. I would just change the caption. But in this particular case, I don't really want any of my edges to have labels. So I'm just going to go through, select each edge and untick show label. And I can do the exact same process with my vertices. The layout is the same when I change the names of my vertices. Once I'm finished with that, I can just X that away, and that gives me a bit more room to play. If I want to move things around, I want to choose this move icon, and this allows me to make an isomorphic graph. So I can drag A over here. Now, the network hasn't changed. Every single edge that was in that original drawing is still in this drawing. It's just that it looks a different shape. and I could put, say, for instance, D over here. So that's the exact same network that I started with. It's just now a different shape. And so the advantage of doing this in GeoGebra, it's very easy to play around and come up with a very neat way of drawing your network. In this particular case, the neatest one I'm going to come up with is something where I put A in the middle. What we're generally looking for with a network diagram is to avoid, if possible, or even if you can't avoid, just reduce the number of times that edges cross each other but not at a vertex, because that can be confusing. People get confused about whether or not there's a vertex there or not. Whereas in this situation, it's very clear that the only there's only place a vertex can possibly be is where the vertexes are. So if you're designing a network graph and after you've drawn it all up, it looks a bit sort of like this, you would just play around with it and see, is there a simple way to display this graph to make it as sensible as possible? And in this particular case, you could square it up if you wanted to square it up. So that's how to use GeoGebra. Have a bit of a play with that. You'll find with the assignment, if you can use GeoGebra, because you can save and because you can move things around, it's a lot better than continually having to redraw a graph from start. So going back in, I won't actually draw those there because you can draw a couple of examples on there, but because we've just done that in GeoGebra, I won't go through that now. Now we can also draw network diagrams from tables, and for that we look at which if the connections aren't mentioned, we just assume they don't exist. Sorry about that. So in this particular case, Anna is joined to Bree and Denny, but no one else. So we just assume that there is no connection between Anna and anyone else. Now, for instance, we can start with Anna, and we could start with Bree over here, and the join between them is going to be 5, because that's how many number of minutes between the houses. And Anna also joins to Denny. Well, we'll go with Eve first. So Eve joins to Bree, and that's 6 minutes. So we've done that one. We've done that one. Kate joins to Eve. So if I put Kate down here, C for Kate. Kate joins to Eve, and that's, there we go, 2. I might just make a nice bigger, I probably should be using a different colour, but either way, it should make it very clear where your vertexes are. So I've done that one, and Kate joins to Bree, and that one has a weight of 3. So I've done that one. Danny joins to Anna. I'm going to put that one up here, and that distance is 2. And Danny also joins to Bree, and that one's there, and it has a distance of 4. Okay, now there's other ways you could have put that graph together, but that way I think is relatively clear. I've got no crossed edges that aren't at vertices, so that's all good. Now, importantly, when we're using computers, and network theory is used a lot with computers, we need to be able to put it in some form of table for a computer, because a table is not going to understand a network diagram. But here you can see a couple of examples of how a network diagram could be represented in a computer situation. These are both the same. So between A and B there's a connection and it's 5 long, but between A and C there is no connection. Okay. Now this next example, you'll see I've crossed out then construct the associated table, because there's no weights given here, so we can't. But in this particular case, when we're drawing a network of the rooms in a house, and this is really quite important when we're designing houses, network theory is used to determine the distance to an exit. And the idea being that if you have to go, the more narrow doorways you have to go through to get out in a fire, for instance, fire needs something to burn, so fire doesn't generally fill a big open space unless there's a fuel in that big open space. But it does certainly burn down walls and those sorts of things. So doorways can be an impediment to how quickly you can exit a house. So these things are measured to determine how quickly or how many connections, how many rooms a person's got to go through in a situation where there's a fire, and whether or not there are rooms that have only one way of getting out, particularly if it's long. So if we think about this, if I'm here in the kitchen, there's only one door off the kitchen, and that goes here into this hallway. So there's only one way out of that kitchen. There's only one way out of the pantry. There's only one way out of the laundry and storage room. There's only one way out of this bathroom, and all of those lead into this hallway. From that hallway, I can go out into the entrance, and from the entrance, I can go outside. But also from the entrance, I can go into the formal lounge dining. There's 2 exits off the formal lounge dining. I can also go to the family room, and from the family room, I can go outside. So when we're drawing our graph, and I'll just make this a little bit smaller, when we're drawing our graph of this, we would also create a vertex for the outside. Now, in this particular case, we've got a whole bunch of rooms that all join onto the hallway. So I've got the kitchen, I've got the pantry, I've got the laundry, and I've got the bath, and they all join onto the hallway. And the hallway joins to the entrance. The entrance where joins to outside. I'll put outside down here, and I'll call it O. So the entrance goes outside. But from the entrance, I can also go to the lounge dining. And from the lounge dining, I can also go to the family room. And from the family room, I can also go outside. And as well as that, from the lounge dining room, I've got 2 ways of going outside. There's 2 doors. Okay, so it doesn't matter where we end up outside as long as we end up outside. So there's a network drawing showing all the possible ways to get outside. So you can imagine that if you're in the bathroom, or even worse, the kitchen, you've got to go through 1, 2, 3 doorways to get out of the house in the case of a fire. So this might be something where the local council, when your plans are put into council, might say, well, no, this house needs further exits to be fire safe. They would have their own rules on that. But these things are modelled using network diagrams, or at least network theory. And then finally, directed networks can have this from and to. So as well as having weights on the edges, directed networks say that travel has to happen in a certain direction. So if we drew this particular one up, I can move from A. I can move from A to B. But that's in that direction. And so that's a weight of 2. I can also move from A to C. And that's a weight of 4. From B, I can move to C. And that's a weight of 3. From C, I can move back to A. And obviously I've got to put, I better put the label on there. It was B2C. So I can move back to C. At that time it has a weight of 5. And from C I can also move to D. And that has a weight of 1. And then finally from D I can move back to C. That also has a weight of 1. And I better put my D there. Okay, and the advantage, like I said at the start of this video, the advantage of drawing that up in something like GeoGebra is if I don't like how that looks now, I can now drag and drop my little vertexes around and make it look a little bit neater. But yeah, so that's what we're going to be doing in today's questions. Just find a way of getting your networks to come to life. Have a go at doing at least one of them using GeoGebra and maybe cut and paste that into your OneNote. You'll find once you get going with that, it's a really nice way of putting that together.